In section 4.8, we're actually going to look at three objectives, 19 to 21. And instead of stretching the graphs this time, we're going to translate the graphs. And what we're going to do is write equations and talk about the phase shift and vertical shift, so that vertical translation. You're going to graph a function, given an equation without the calculator. You're going to actually state the phase shift and the vertical shifts given an equation. So it's just going to be a lot of going forward and backwards from graphs to equations to ordered pair rules. Now I want to see what you remember from when we did translations back in the earlier chapters. Take a moment and look at these four equations here and then the four sets of words that go with it. Pause the video and see if you can match up which words go with which equation. Go ahead and pause and the answers will be on the screen once you're done. Okay, did you get it right that it's DBAC? Here's what you want to remember, and we're going to go through this in the notes. If you look at what's grouped with the x, in this case it's x plus 14. The x-axis moves left and right, so this is a left or right slide. It is just the opposite of what you see in the equation. So therefore this equation says actually slide the thing left 14 units. Conversely, this guy here is grouped with x minus 14. Just do the opposite of that. That one's going to say go to the right. Now 2 and 3, what you're going to see, that 14 has nothing to do with the x. It's not grouped with it in the parentheses. If I rewrite it the equation-wise, I would subtract 14 for this one, get y minus 14 equals the sine of x, and then look at it backwards from there. This says don't do minus 14 to the y, which goes up and down, but do plus 14. Plus 14 would say move that graph up 14 units. And then the last one right here, this actually says move it down 14 units. There is a shortcut trick in this. In Algebra 2x, you learned that the x movement is always backwards, but the y movement is what it looks like when it's written in this format, and that also will work in this case. So let's first recall that another word for a translation is to slide a function. And we learned earlier in the year that the translation rule can be written as an ordered pair rule, where you're going to add a value or subtract it from x, or add or subtract something from k. This is called the translation rule. And this is literally what happens to a graph. So whatever the ordered pair rule says is what you will visually see happen to the graph. In trigonometry, we don't necessarily call this a translation. If it is slid left or right, there's a specific word for it in trigonometry. It's one of these four words down here, and I'm going to tell you it's called a phase shift. We're first going to look at phase shifts, and then we're going to switch gears and look at vertical shifts, or vertical translation, which is the up and down movement. So you do want to be familiar with, if they ask you to find a phase shift, you have to realize they mean the left or right slide. Now let's look at this graph really quickly. This is a cosine function. If I look at just one cycle of cosine, which goes from 0 to 2 pi, I notice in this red graph, its starting point is now right here. They actually slid this graph. They slid it over pi over 2 units, or 90 degrees. So if I wanted to, I could write the translation rule for this. The translation rule for its ordered pairs would be that the x's are having a pi over 2 added to them and nothing for the y. Now we're just going to do lots of examples, and here's a good one. This is written in function notation, so this is it right here. Here's the function. If it helps you, just think of it as y equals instead. So y equals the sine of x plus 60 degrees. They want you to identify the phase shift. First thing I want us to do is I do want us to be able to draw this by hand. So let's talk about what is the parent function. Remember, the parent function is the most stripped down version of the graph. And if we strip this down, the parent function is going to be y equals the sine of x. The translation rule for this is I can tell that the number being added to it is grouped clearly with the x, so this is a phase shift. Now, is it a shifting to the right or to the left is the question. What we always do is just group everything with its variable, either x or y, and read the opposite. So since it's x plus 60, it's really x minus 60. And for x, that means it's left. So it's really going to be moving it left 60 degrees. How do you write that as an ordered pair rule? I'm going to say take the x's and subtract 60 degrees from them. The y's, nothing. There's nothing going on with that. This is the wording you would use for the phase shift, and again, this is the translation rule for that. By the way, if this was in radian mode, the rule that we would use is, say, take your x's. Remember, 60 degrees is the same as pi over 3. That would be the translation rule in radian mode. And then let's complete the language here. The phase shift is just left 60 degrees. Now let's sketch this by hand without a calculator. I like to start this by, again, we identified the parent function for a reason. I'll sketch one cycle of the parent function. Remember, the sine function has a period of 0 to 2 pi in which it makes a complete S shape. It starts at the origin and it ends at 2 pi. Halfway in between is where it cuts through. This graph is nice symmetry. To make the S shape, between 0 and pi is half of a pi. It peaks out at 1, is its amplitude. Between pi and 2 pi, which is 3/2 pi, it bottoms out at -1. And that is what the parent function looks like. Now all they want us to do is to take every ordered pair on here and move it back 60 degrees, or because I'm in radian mode on this graph, back pi over 3. Now 1/3 of a pi is smaller than 1/2 of a pi, which is right here. So I want to take this point right there and just move it back about 1/3 of a pi. And that's appropriate enough for now. Take this ordered pair at the peak and move that back about 1/3 of the pi. Take this one here, move it back 1/3 of a pi. Take this, about 1/3. Take this, about 1/3. Connect those new dots. And what we're going to get is the function of sine of x plus 60 degrees. And we're done. This next example is a very good word problem example on how to interpret it in a real life. So let's go through it. Great example if you're going to become an electrical engineer. And electricians tend to use phase shifts. So here it is. Maximum inductance in an alternating current occurs when the current flow lags behind the voltage by pi over 2. So something is lagging by a pi over 2. In a situation of maximum inductance, find an equation for the current and sketch the two waves. Assume the two waves have the same period and amplitude, and that the voltage is modeled by the equation y equals the cosine of x. So we can sketch the cosine of x, and then what they want us to do is graph maximum inductance. So here's maximum inductance. They want it graphed. They're telling us also graph voltage, but use this equation for voltage. So let's just graph the voltage first. It's a cosine function. Again, cosine has a period from 0 to 2 pi. Its amplitude is from 1 to -1. And it makes a C shape when it starts. So it actually starts at 1, and it ends at 2 pi, which is right about here, which is there. Halfway in between is pi, that's where that bottoms out. And it cuts halfway in between here on the axes. So this here I'm going to label is voltage. Now the hardest part of this is just interpreting the language. Maximum inductance, here's what it is. It's when the current flow lags behind the voltage by pi over 2. So basically we're going to take the parent function of voltage, which is y equals the cosine of x, and we're going to do a translation that interprets a lag of pi over 2. Now this is a real life problem where this is the time right here, the time aspects. If this lags behind, look at the 4 choices. One of these is the correct ordered pair rule for lag. Pause the video and see if you can guess which one of these 4 ordered pairs will give us or help give us the equation for the inductance. Okay, if it lags behind, what it means is if this is time, that time has gone by. So if this is where we start here for time, if time has gone by, time has moved this way. So that's where it's going to start at a later time. So what we need to do is take the voltage graph and actually shift it to the right by pi over 2. This translation rule will shift it to the right. So I would say the translation rule is take the x's and add to them pi over 2. Don't subtract. You think the word lag means to subtract. And it might in a general graph, but this is a word problem and it has a context to it, which is time. So again, if this is where time is 0 and time starts, this is where you're going to start later on as the clock is started. Now to write the equation, it's very easy. The ordered pair rule says take x plus pi over 2. That's exactly what happens. The ordered pair rule is literally what's going to happen. To force the equation to do that, you take your parent function, and we're going to subtract from the x pi over 2. That is the equation of inductance. And then to graph inductance, what we're going to do is just take the various ordered pairs here and shift them to the right pi over 2. So this guy's going to shift here. This is going to get shifted here. This guy goes here. This one here. And this here. So this blue graph is the maximum inductance. Kind of a tricky problem because most people want to take the red graph and shift it backwards before to show the lag. But because, again, it's a real life problem, it goes forward. Now this slide here is just giving you the phase shift identity. And all it says is that if I wanted to find the sine function, which is, remember, one cycle of it looks like an S, that's actually the same as the cosine of x minus pi over 2. What this right here is a shift to the right of pi over 2. So if you take cosine and shift it to the right pi over 2 units, you will get the sine function. Another theorem is just this right here. If I wanted to get the cosine function, that's the one that makes the C shape. Cosine is take the sine function and do x plus pi over 2. Or take the sine function and go left pi over 2 units with that and translate it, and you will actually get the cosine function. Let me show you that first theorem. The first theorem says take the sine function. This is one cycle of sine right here. Okay. Now this right here says if you take the cosine function and do x minus pi over 2, or take the cosine and slide it to the right pi over 2, you're going to get the sine function. Well, this right here is the cosine function. If you take this graph and take all the points and slide it to the right pi over 2, what's going to happen is you're going to actually get this graph here. Let's just look at another example and do a sketch by hand. Consider the graph of the function f of x equals the cosine of x. They want us to find an equation for its image under the translation of x and then y minus 2, and then sketch that graph. So let's just go ahead and find an equation for the image. This one right here, the translation is actually dealing with the y. And when it deals with the y, this is actually called a vertical shift. It's no longer a phase shift. So any movement to the y as a plus or minus is a vertical shift. So if they ask you that, that's what they're referring to. All you need to do is take the original function, and let's just go with what I have written here. Let's jot the parent down. The parent's the cosine of x. To find the image, we just do the inverse to everything. To find the image, I'm going to go to the y and I'm going to add 2. So it's y plus 2 equals the cosine of x. Clean this equation up, I would subtract the 2 from both sides and say it's y equals the cosine of x minus 2. Be very careful and do not think that the x and the minus 2 go together. Sometimes in pre-calculus they will write this equation as y equals negative 2 plus the cosine of x to keep the vertical shift and the phase shift kind of distinct from each other. Now let's sketch it. Cosine function again, we know makes a C shape from 0 to 2 pi. Bottoms out at negative 1 and kind of cuts here. I always like to start with the parent, and I'll just write that that's the parent. And then what I need to do to this graph is literally this ordered pair. This is actually what happens to the graph. The y's are being minus 2, so the y's are shifting down 2. So be careful with the tick marks. If you take a look at this, they're kind of labeled by thirds here, so let me extend this out a little bit more. This would actually be negative 2 right there. So I'm going to take this here and I'm going to shift it down 2. So from here I go 1, 2 is the new point. I'm going to take this guy, which is sitting at 0, and move it down 1, 2 at this point. This one's going to come off a little more. This guy here, down 2. This one here, down 1, 2, right there. And then if you connect those, this is the new graph. This is y equals the cosine of x minus 2. Now part B wants you to find the amplitude and the period of the function. The period of this function, as you can tell, hopefully, its cycle shape of making a C still goes from 0 to 2 pi, or it's 2 pi units long. Its amplitude, this is how you look at amplitude, is if you take this original graph, if you look at how high one hump is, one hump here is 1 unit high, this hump is 1 unit high. Do the same thing. The amplitude is not 2 here. What you want to do is kind of cut it in half and visualize how high that hump is and how high that hump is. This hump here goes from -2 to -1. The difference is 1. So the amplitude is still 1 unit high. And I'll tell you this, a phase shift or a vertical shift just on its own will never change the amplitude or the period of the original parent function. Only scale changes do that, and you can clearly see that in the graph. This example actually switches gears. They want us to find the equation for the translation of the graph of the cosine function. So we have to go backwards. Now the only thing the problem really tells us is that the parent function is cosine originally. So I always will sketch in one cycle of cosine. Again, C shape from 0 to 2 pi. Bottoms out at -1. I like to sketch that in. That's the parent. Then I go to the function they've given me, and I mimic just that same cycle, that same C shape. So if I look here, I can find that same C shape right here, from there to there. And then I look at it and see how did I switch from the red graph to this new black drawing here. And you can tell this right here. This point here is at 0, 1. And you can tell what's happened is it went down and over to this point. Okay, how much did it go down? You can tell on the y's, it went from 1 to 0. That's how the y changed. And you can tell on the x's, it went from 0 to -pi/4. So what I'll do is I'll write the translation rule. Because the translation rule literally tells you what happens to the graphs to each ordered pair. And look at the graph, you're going to actually literally see what happens. I see that the graph went down, so it went down 1, so I say it's y minus 1. And then I see that it went left pi/4, it looks like. So it went left, which is backwards. There, pi/4. That is literally what happened to the graph. So if they asked me in words, I could say it shifted to the left pi/4 and down 1. Now to write the equation, I take the parent function. In this case was the cosine of x. And I just do everything backwards. To the y, I go and I add 1. To the x, I go and I add pi/4. And here I make sure to kind of group it so I know that the pi/4 is with the x. Clean up the graph. The final equation should be y equals. So subtract 1 from both sides. So it's y equals the cosine of x plus pi/4. Keep that grouped in parentheses. And then minus 1. That is the equation of the above blue graph. Okay, yet another example. Here they want us to identify the phase shift and vertical translation of the graph y equals the sine of x. So we know that's what we start with. So that the image is this. Here's what I would do. They want the phase shift. And then they want the vertical translation, or sometimes they'll say vertical shift. The phase shift here, if I want to, I could actually write the translation rule, even though they didn't ask me for that. The translation rules, it's just the backwards from the equation. Remember the equation's opposite, so it's x minus pi/3, so it's really x plus pi/3. And the y, what I need to do is regroup that 4, so I would say it's really y minus 4 in the equation, and kind of group it with that. So what's really happening in the equation, if it's y minus 4, what's really happening is y plus 4. Or again, the shortcut, algebra 2xers, you might just do exactly what you see for the y. Now they want me to identify the phase shift, so I need to be specific because I don't know what the x and the y ordered pair really tells me necessarily. So I would say that the phase shift is it's going to move to the right, pi over 2 unit, or pi over 3 units, and the vertical shift is just going to go up 4. Now, if you felt comfortable doing this on the previous slide, you may not have to listen to the whole thing, but what I'm going to do is challenge you to do this. Find the equation for this graph. Sketch the parent function, and let's use, I think we're going to say y equals the sine of x as its parent. I want you to sketch the parent function, think of what the translation rule would be, and then from there, write the equation. Pause this video and try it, and then when you restart the video, I'm going to have all the information right in front of you. So go ahead and pause it and give this a try. Okay, here's what the answer is. Right here in the red is the correct equation. If you got that, great. If not, let me walk you through it. I sketched the parent function right here. And what I did is I found a pair that I could mimic. I looked at this ordered pair and this ordered pair right here, the first hump. Because when I went back to this graph, I realized that if I have to mimic the sine function, it's going to be something like that. That same blue shape is the same as my red. I found one ordered pair I could compare. I realized I could compare this ordered pair with this one. So what I could do is I could see that this thing is actually moving. It looks like to the right a little bit and then up. To figure out exactly how much to the right and how much up, I just compared the ordered pairs. You're going to see my work right here. For the y part, I noticed I went from 1 to 4, so the difference between 4 and 1 is 3. So it actually slid up 3. So it went y plus 3. The x is a little trickier. I can tell it goes to the right a little bit. And it goes to the right by how much? Well, it changes from 2/3 pi from its original 1/2 pi. So I subtracted those two values. I took 2/3 pi minus 1/2 pi. They're just fractions. I need a common denominator. I made a common denominator of 6. So I end up having 4/6 pi minus 3/6 pi. The difference is 1/6 of a pi. It moved it to the right, so I wrote plus pi over 6. Now what's written here in the blue, this ordered pair rule, is actually what happens to the graph. So I'm just going to check. This says the graph goes right pi over 6 and up 3. And I would agree, right pi over 6 and up 3 seems reasonable. I then went to the equation here on the bottom, and instead of adding 3, I subtracted 3. And instead of adding pi over 6, I subtracted pi over 6. Then I cleaned up the equation and I added 3 to both sides, which got me this final equation here. 2 more graphs for us to look at. This is a nice example of tangent. The graph here represents a translation of the image of the tangent of x. This one's a little trickier because we don't use tangent as much, but what you want to remember is that tangent has a period. When you go around like the unit circle, if you think about it, the tangent's the slope of the line. We know from here to here slopes are undefined. So they're undefined, that's where you're going to see an asymptote on the graph. This is really the connected cycle of tangent that we see. So each kind of swoosh that we see is going around the circle each half time. And this happens between pi over 2 and negative pi over 2. So the parent function for this starts at the origin, which is right here. And an asymptote drops down about right here at pi over 2 and at negative pi over 2. So what happens is one cycle looks something like that. Now what I want to do is just compare the turning point on that and see how it changed. Now the one thing I know about tangent is when x is 0, this ordered pair, the tangent itself is 0, which is really this right here. When x is 0 degrees, the slope of that line is 0 degrees. So that's what that ordered pair mimics. They're telling me on this graph, though, when x is 0, they had 1. So it's a really not much going on there. What you're going to be seeing is that it is actually sliding up 1. So it's going to be the translation rule that I would write. Let's extend it out here. Nothing to the x, but the y is just going to be plus 1. The parent function is y equals the tangent of x. To make this equation do that, all we need to do is take the y and subtract 1 from it, and then clean up the equation. So it's y equals either 1 plus the tan of x is a pre-calculus way to write it, or y equals the tan of x plus 1 is what our book will do, but be careful and realize that the x and the plus 1 are not connected together. And notice this, the graph, from the red graph to the black, it shifts up 1. The shift up 1 in the graph right here should mimic the actual translation rule. Okay, and it ends up mimicking it here also in the equation, just because when we take the opposite and clean it up, it becomes the actual number there. Here's the last problem we're going to look at. Consider the function y equals the cosine of x minus pi plus 1. What they want us to do is to graph this function using the calculator in part A. And they want us to go from negative 2 pi to 2 pi. So that means go from here to here only. We have to just sketch that. And then they want, on part B, use the graph to find the coordinates of the points where the function attains the maximum. And then part C, use the graph translation theorem to explain how we could also find these points without the graphing function. Now the first thing I want to do is just have you practice to graph this function without a graphing calculator. We're going to deviate a little bit. So I want you to take a few moments and take a look at this equation and tell me which one of these 4 translation rules is correct. So take a moment, pause the video, and see if you can pick the correct of these 4. Okay, hopefully you discovered it's letter D. This graph right here is actually going to, if you take the parent function of the cosine of x, if you take that graph, we're going to move it pi units to the right, and then we're going to go up 1 unit. Remember, what you can do is regroup it. So to regroup, I would move the plus 1 over and subtract 1, and then do the opposite. So instead of y minus 1, it's actually y plus 1, and instead of x minus pi, it's x plus pi. Now let's graph it by hand. They want us to do from negative 2 pi to 2 pi. That's 2 complete cycles. So let's go ahead and sketch the parent function of cosine for 2 complete cycles. So the first thing is going to give us from negative, starting here at 1, and we're going to get something like this. And let's just go one more time from 2 pi to 4 pi. Now that's the parent function. So let's take that graph, and what I want to do is actually move forward pi units and then up 1 at the same time. So I'm going to take this point here, move forward from 0 to pi, and then go up 1. So that's where that starts. Then I'm going to take this point right here, and I'm going to go over again pi units and up 1. And take this guy, go over pi units and up 1. Let's go to this next one, pi units and up 1. This guy here, pi and up 1. Now if we connect those dots, we're going to have 1 cycle of cosine. And then what you would do is just repeat that, and let's go backwards because they want us to go all the way to negative 2 pi. So I'm going to pause the video and sketch that in real quick. So now that we have the picture of the graph, I just am going again, we want to look at just from here to here. Answering in part B, find the maximum coordinates. We can tell it maxes out at negative pi and at pi, so that would be our answers there, is where it maxes out. And then use the graph translation theorem to explain how you could have come up with these points without graphing the function. And to do that, what you could have said is that the parent function actually maxes out, for example, at 0, but the translation rule tells me that I would have to move forward pi units and up 1. So if I take this point and move forward pi units and up 1, it lands me at pi. And then because we know the cycle of cosine is every 2 pi's, that if I go backwards a whole 2 pi length, I would also land here. So that's how you could do it. Good luck on the homework, and let me know what questions you have.